Welcome to the New Jersey Astronomical Association. We're glad to present to you this month a presentation by Steve Indyk, who is, by the way, a longtime member of the New Jersey Astronomical Association. Steve Indyk is a senior engineering manager at Honeybee Robotics. Honeybee Robotics creates advanced robotic systems for the world's most demanding environments and applications. Since 1983, they have completed more than 300 advanced projects for NASA, the U.S. Department of Defense, academia, industry, and others. Be advised that Steve is monitoring the YouTube channel chat box and will be answering your questions during and after the event. So we're going to switch over to Steve at this time. Go ahead.
Great, thanks Jim for the nice introduction there, and thanks everybody for joining. And I hope you get some good information from this presentation. I've been looking forward for presenting to you all for a little while now. I've been with Honeybee for about 8 years. I've worked on a lot of very exciting NASA planetary missions. And today I hope to share with you some information from those missions of the past, what we're developing for the future, and what we're looking forward to beyond that. I'm going to focus a lot on sampling systems for planetary and astrobiology sciences today. I guess first, as Jim mentioned, I'm actually a longtime member of the NJAA. I got my start in the Voorhees Astronomy Club that was led by Mrs. Bellows back in 2003, 2004. So, you know, my advice to everybody out there is always force through the students, because you never know what their true interests may lie, and you could be the one to help them discover their real passions. So since my days at Voorhees, I've had a lot of great experiences since then. Like I said, I started with Honeybee Robotics about 8 years ago. One of actually the very first project I worked on was the Opportunity Mars rover, and that really piqued my, to me that was the best experience I had as a young engineer, and I really did get to work with some excellent people. Some of them in that lower picture there, and right in the center of that is the Opportunity in Spirit test bed that we would do a lot of our testing on for the rock abrasion tool. In a moment. But you can also see some of the other great NASA scientists and engineers that I've gotten to work with on a lot of other projects. And if you guys are familiar with that big hexagon behind me, that's not the Honeybee logo. That's actually the James Webb Space Telescope behind me, which I got to see at my time at NASA. But that's just a little bit about me. I'll start talking a little more about sampling in space. First, it's pretty difficult. You figure on the ground on Earth, you can do a lot of different methods to collect sample. You can drill, you can shovel, you can dig, sieve. All these things are pretty easy to do. But getting out in the environment of space, it's pretty difficult. The Apollo astronauts had a lot of difficulty trying to drill and take core samples on the moon. Anywhere outside of that, it's had to be done robotically, and those are some pretty big challenges. Honeybee has done a lot of work related to sampling and sample sciences and how you present those samples to scientists for a very long time. And the very first mission that Honeybee really had that demonstrated our capabilities is the rock abrasion tool on the Spirit and Opportunity Mars rover. Opportunity ended its mission about 2 years ago now. It's hard to believe it's been that long after about a 14-year run when it was only supposed to be there for about 90 days. So Honeybee provided the rock abrasion tool, which is the grinder you can see in the lower right of that image. And here you can see some of the work that it did in Mars back in just 2012. Here are some brushes and some grinds on the Martian surface. It's my understanding that one of my colleagues, Jim Rice, spoke with you guys about a month ago. I had the opportunity to work with Jim on Opportunity's mission for the past 6 years for it, collecting data and grinding some of everybody's favorite Martian targets. But I like this slide here because you can really see the variety of samples that are dealt with in space, specifically on Mars. You can see some very rough terrains. Texturally, these are all very interesting images. You can see Kirkwood in the upper right there. Those are some of those famous. Those aren't the blueberries that are made famous. Those are the newberries, because when we came to that target, we didn't even know what they were. They looked like the old ones, but they had a different composition altogether. So we just named them newberries. And you can see some very sandy surfaces that we had to dust as well, dust off with the brush on the rat. It's a very capable scientific instrument. Here you can see a nice table of all the different targets that we contacted on Mars with opportunity and ground, and we can get some hardness information from the grinder itself. The grinder, the rat, is basically a geologist's hammer. It's used to break open the rocks, and instead of a hammer using a lot of energy coming down on it, it uses its energy through a grinding motion to break open the rocks so the other instruments can then view it. So like I said, this is Honeybee's real first entry in planetary sample handling. And it's not an easy task, and this instrument lasted for 14 years in the environment on Mars. Moving on to something a little more dedicated to trying to acquire the sample. The Martian soil has a lot of ice water in it. As was discovered in the Martian poles by the Phoenix mission. It landed, and Honeybee provided the ISAD. It's the scoop. And actually, what most people don't know about the scoop is that it's actually not just there for scooping. It's got a rasp on the bottom of it. You can see that rasp in the lower right-hand image. That's for scraping the hard Martian surface, especially hard ice. People underestimate the difficulty of sampling ice in space. It's out there. If you melt the stuff, it has the chance it could refreeze on you. And that was one of the problems that the Phoenix scoop had. So you can see the rasp is at the bottom of the back end of the scoop. It's actually kind of more complex than it may appear. The rasp scrapes the surface, collects sample in the back of the scoop through that little hole you see, and then through a series of wrist actions, it passes that sample to the front end, the bucket, right? And then that bucket is what drops the sample into the Phoenix instruments. Actually, during this mission, some of that sample got frozen and stuck inside the scoop, and that caused some headaches at JPL and NASA as far as trying to get that sample into the instruments. So again, this kind of shows that even with great success in other instruments, it's still a very difficult thing to acquire sample on planetary surfaces. And then most recently, and still in operation, we have the Curiosity Rover, Mars Science Lab, MSL, and this has two very nicely designed engineering implementations from Honeybee on sample acquisition and sample handling. So first in the upper right, similar to the rat, you have the DRT, dust removal tool. It doesn't have the grinding capability that the rat did, but it's a really excellent brush at sweeping off dusty rock surfaces. The rover itself has a drill on board. I'll get to that in a moment. And then you can also see the SAM instrument, that gold box in the upper right. I've been an operator of the SAM instrument since just after landing of the rover. And right below that big gold box, you can see the SMS, the sample manipulation system, which was also built by Honeybee. And I'll go into a little more detail about that one. But that's a 74-cup carousel for handling those drill samples. So Curiosity itself is a little different than the other missions that I just mentioned. It's an astrobiology mission, really. It's got the SAM instrument, which is a very nice mass spectrometer. It's one of the most sophisticated instruments put in space, let alone on another planetary surface. And it's there to try to identify if the Martian surface is habitable. It's there to detect organic compounds, if there are. And I'll explain a little more about that in a moment, but that's kind of the, that's kind of the reason right there why we care about sampling on planetary surfaces. Are there organics? Are there, I don't want to say, is there life out there? Because our capabilities, our engineering capabilities today can't determine if there's life out there, but it can tell you if there's the building blocks of life. And that's really the goal of the SAM instrument. Great, thank you. I'm really happy to be here. I'm glad you guys can join this live stream, especially given all these weird pandemic conditions. So thanks for participating. So moving on with some MSL. Here's a nice picture of the drill at its full extension. It's kind of an interesting device for collecting sample on the Martian surface. You see those two prongs on either side of it. Those are the stabilizers. So that's how the drill braces itself on the Martian surface, on the rocks that it wants to sample. And in the center, you see the drill itself. It doesn't look like a standard drill bit, right? Like what you'd think of for drilling a hole in a wall or an auger, right? You see it's got that sleeve on the outside of it. Inside that sleeve is the auger. And the drill bit on the end is what pulverizes the Martian rock and then passes it through that sleeve and then into that inner housing where, again, through a series of, there's a mechanism in there called chimera, it passes the sample to a sample drop-off, which then can be deposited inside the rover body where the SAM instrument is. It's a kind of interesting design. It's complex, and it's done a good job so far. Recently on the mission, the drill is actually stuck in that position that we see right now. That's because there was a mechanical fault with a subcomponent of the drill, which has made sample handoff difficult. Again, similar to the Phoenix scenario, right? It's really not about getting the sample in some of these cases. It's also about passing that sample to the instrument and how can you make that happen and how do you make that reliable? The biggest problem that we've had with the mission so far in this sampling chain is quantifying that sample when it comes out. The SAM instrument is a very specific, it's best for the scientists if we know the quantity of material. JPL spent a lot of time and energy quantifying the amount of material that's coming out of the drill in its original configuration and in this new FEST, they call it, configuration for doing the sample drop-off. Even with some of those problems that we've experienced, here's a current count of the drill holes that we've had on Mars to date. I always love these pictures that the team puts together for it. There's a really big science team for MSL and a lot of really capable people. And these images, I think, really tell the story of what we're looking for on Mars. They look like holes, right? But when you look at the details, that's where the real interesting part is. I'm not a scientist. I work with a lot of really brilliant scientists, and they can tell you a lot more about these samples than I can. But just at a first pass of it, the thing that stands out to me is not all the tailings from those drill holes look the same. I see a lot of grays, and I see a lot of reds, and I see some browns in those tailings. And those tailings are what we're sampling and what the scientists are going to analyze, right? So what does that mean? And I'll tell you, the science team doesn't get very excited when we see red tailings. Red tailings looks like the surface of Mars, oxidized material. It's those gray samples that really perk people's interest up. If it's gray, it's not oxidized. If it's not oxidized, it could still carry organic compounds that we want to know about. And just at the bottom of this slide, I have a little footnote. You can see the scoop at the bottom. We can actually scoop material as well as drill. And you can see one of the images of what it looks like on the end of the robotic arm to place the drill on one of the Martian surfaces. And then just because it's always a fun note, we've driven over 21 kilometers so far, and you can see the traverse from where we landed at the Bradbury landing site to where we are today. The Planetary Society has a really excellent blog that I highly recommend for keeping track of the most recent big scientific achievements on MSL. It's a really up-to-date and great part. Great asset. But I'll stick to what I'm best at, and that's planetary sampling stuff. So this complex diagram is inside the SAM instrument, and that is the SMS, the sample manipulation system that some of my colleagues at Honeybee constructed, and I've had the pleasure of operating. So in here are 74 different types of cups that hold those samples that we just drilled from MSL, and we deposit in these cups, and then we go through a series of pretty complex operations to analyze them with a mass spec, a tunable laser spec, or some gas chromatic, or through gas chromatic GCs. Oh my goodness. But here's a good diagram of what the SMS looks like, and then all the different capabilities and samples that we can hold in it. there's a pretty unique experiment that we can do with the SAM instrument, and that's derivatization, wet chemistry for easier pronunciation. And what that is it's very foreign to me. It kind of looks like French, but it's a very complex analysis where we're bringing up a chemical, a very carcinogenic chemical that binds with any organics that we might find. So you can kind of think of the Martian sample as a caterpillar in that analogy, and then the wet chemistry fluid is the derivatization agent that allows that caterpillar to go through its chrysalis stage and then turn into a butterfly. And that butterfly is the organic compounds, these very heavy then organic compounds that the rest of the mass spec will then analyze and determine if it is of real organic chemistry note. And then that gets the scientists very excited and makes their day a lot easier because then we can really say that the mission really discovered something very important on the surface of Mars. With that, here's a nice picture of the rest of some of the other members of the SAM operations team that makes those sort of analyses happen. It's a very demanding job to make these sort of scientific discoveries and make it all happen. And these are the people that are kind of behind the scene that make it work. We go through long days of planning. You can see in the one image there, it's an 8-hour planning cycle to make one uplink happen. We typically do one planning cycle for one day, Monday, Tuesday, Wednesday, Thursday, and then Friday, we typically do a 3-day plan to cover the weekend. So the rover is often, very busy and has a lot of work for it going on. And we do all this relay work through the Deep Space Network, the DSN, which is a collective around the world between Spain, located in Spain, US, and Australia. That is able to relay all this information and collect our data from the Martian surface and bring it back to us. Of course. Oh, no, not at this part of it. We actually do use pyrotechnics on the lander. If any of you remember the 7 Minutes of Terror, there's a few frangible bolts, explosive bolts that deploy the system onto the surface. But pyro here, that's actually the pyrolysis oven. I didn't go into SAM detail. Actually, I think you had Melissa Trainer here a couple of years ago that gave a great SAM presentation. But there's 2 pyrolysis ovens, and that cooks and heats the sample that we collected. So it vaporizes some of the sample material, and that hot gas then is transferred into the rest of the mass spec. So we carry two pyrolysis ovens, one part for redundancy, and 2 part because we can do slightly different temperatures with them. Great. So I'll move on. I'll move out of Mars for now, and I'll start talking about how we make these sorts of things happen. And a lot of that comes down to analog. One of the pleasures of my job is I work with a lot of really smart scientists. And I'm not a scientist. I'm a reasonable engineer. And it's my job to make these really smart scientists' dreams come true, make them realize what science they want to achieve, and really push the limits of what we can do in space. And a lot of that comes down to, furthering their instruments, furthering the capability of their instruments, and in NASA speak, increasing their TRL level, and that's technology readiness level. So that's bringing something from a concept that's just a whiteboard idea, a TRL1, bringing it up to a flight unit, which would be a TRL10. And in between that, we have to go, we have to CAD those sorts of material. We have to CAD that. That would be, if we CAD'd their idea, that might be a TRL3 level system. If we can test it in a relevant environment, then that could be a TRL6. And TRL6 is one of those magic numbers that gets NASA's interest because if it's TRL6, it's survived very tough environments. It could survive very tough vacuums, or very, very high vacuum, very high temperatures, or low temperatures. It could survive the rigors of microgravity, of vibration for launch to get it into orbit or onto another planetary surface. But kind of crossing that TRL6 mark is pretty important for instrument development. I work a lot with these scientists to develop their instruments, and mission development and design is another aspect that I'll touch on a little later, but really my focus is on instruments and making those things happen. So here you can see one facility at NASA Glenn that we've used in the past for testing microgravity. It's a drop tower. It's about a 500-foot hole in the ground, 400 feet of which is for dropping one of those red and white cylinders that you can see. That's a drop rig. It's a drop vehicle. We hoist it up, mount it on top of that big yellow tube that you see on the right, and then pump this entire chamber down. It's a huge vacuum chamber, the largest I've ever seen. Pumps out all the air in there. And then we drop that entire rig that weighs about 1,000 pounds, over 400 feet, into a big bucket of styrofoam beads. Think of a beanbag chair. Very similar, makes this really loud crunch and vibrates the entire building. And at most we can get about 2 of these tests a day. So we put some of our instruments inside one of these drop rigs, and then to test the microgravity, test the instrument in the microgravity, go through this entire process and make that drop. You can see the command center for that in the lower right there, where we have some cameras in that vacuum chamber. I don't have a video of it, but it's really gnarly to see all those beads boil in this vacuum. Those beads hold a lot of air at the bottom of this. And this vacuum is so high that you can actually see all those beads just boiling all the air out of it as the vacuum gets lower and lower. But this is just one set of tests that we do to flight harden equipment. We also do a lot of testing. Sample handling requires a lot of in situ work. So for Honeybee, a lot of my colleagues have traveled all across the world in different analog sites for different scientific reasons to test some drilling equipment, test some sample handling equipment. I'll just touch on one real quick, which is one that I got to go to in the Atacama Desert. It's about a 6-hour drive from Antofagasta in Chile. And 5 of those hours are off-roading. We had to take those big Toyota Hilux trucks for a very bumpy 5-hour ride out in literally the middle of nowhere, about 10,000 feet elevation. Absolutely beautiful scenery, volcanoes in the background, to collect samples that are Martian analog sites here. 10,000 feet, it's very dry, very arid. I don't see anything green growing in those hills and mountains in the background. Plants don't last very long out here unless they're very rigorous, robust plants. And one of the tests that we did, I drilled about almost 2 meters deep into the soil before we hit anything that looked that was moist. It's a very tough environment. These are things that we think are also in other planetary surfaces, such as could be on Mars. Here's a picture of that 2-meter long drill, and one of the other drill bits, a coring drill bit here out in the desert. This is just some of the analog testing work that we do. Some other stuff we do is we test sampling systems. So this is a drone that has a scoop at the end of it. I'll highlight the scoop system here. So we were flying this at the high altitude to a very remote location in the desert, and then collecting sample remotely and bringing it back to us. Why would we do that? Well, because I just told you it took about 5 hours to drive out in the middle of nowhere. And once you get there, it's kind of, let me see, I'm gonna try changing over to a video real quick. It's a lot of work to make that. Oh, so is that one working? Here, I think that's it. So here's just a nice video of one of our drones flying in the Atacama. But it's a lot of work. It's a very hot place to be in, very arid, very dry. You dehydrate pretty quickly if you're not drinking and if you don't get enough shade. So we took this drone, we flew it out in the distance over 2 miles away, landed it, collected a sample, and brought it all the way back for our scientists on the field there to analyze and tell us if that area was worth traversing to go collect further samples. So these are just some of the technologies that we work on developing for our various clients to give them better scientific capability in what they're doing. And I'll touch on drones again a little later too with another mission that some of you may know about called Dragonfly. The moon. So I didn't preface it very well, but there's a big push going on right now for the moon. based off of the Commercial Lunar Payload Service Program, CLPS. It's initiated in 2018. The first flight is really expected in 2023. But CLPS kind of comes to us after all these other missions, all these other big classes of missions called like New Frontiers or Discovery or Flagship. Those are all three different classes of mission that NASA puts out for planetary science. This is a pretty exciting year. This is the year of the decadal study. So NASA is funding 10 different projects that NASA will then evaluate, not as missions that will fly, but as kind of the standard that NASA will look at as what is the interesting science in the next 10 years and what can we accomplish with that science with our today's current technology. So that's, again, the planetary mission concept study. And this happens once every 10 years. And NASA funds it for missions all across the solar system. There's a mission that wants to land on Mercury. There's a rover for the surface of the moon that wants to traverse hundreds of kilometers. There's a Neptune flyby mission. There's a lot of very interesting stuff, and those reports are due out in a couple months' time. But going back to the CLPS program, for the big push to the moon, you have some of these private landers that are kind of left over from the unclaimed Google Lunar X Prize, and NASA decided to pick up the remnants of that and support some funding for these smaller private companies to actually reach the moon's surface. So it's a little more than just landing on the surface of the moon. That's a big deal. That takes a lot of effort. But what are you going to do when you get there? You have to get science out of it, right? You have to develop technologies that can survive in the lunar environment and accomplish other scientific goals. So that's where we come in with certain sample acquisition systems. This is not a drill. This is something that we believe is more novel than a drill. It's lighter weight, smaller, and possibly more efficient in this environment than a drill for collecting sample of certain types. This is PlanetVac. This is one system that Honeybee developed using pneumatics in space. Well, isn't there a vacuum in space? Exactly. We're using that vacuum to our advantage. We're basically taking a cone, putting it on top of the regolith on the surface of the moon, injecting pneumatics into that regolith to disturb it, which causes the regolith to then pass up through a tube and then into a sample collection system. So we were selected for flying this concept, this demonstration on the surface of the moon we call PlanetVac from the CLPS programs. This is something that we're currently working on for collecting lunar regolith material. And we've done a lot of tech development and a lot of analog testing. Here you can see Masten. Masten is one of the companies that's part of the CLPS program for providing a lander that's going to land on the surface of the moon. I believe they are currently third in queue to reach the surface of the moon. Here's a video of us testing our PlanetVac system on the Masten lander out in the Mojave Desert. Again, one of those cool field sites. And you can see right there, we're landing inside this big sample bin where we're then going to fire our pneumatics and collect that sample and transfer it into a sample collection bin where we could then place another instrument and then do a scientific analysis with it. Say you want to get a little deeper in the surface than just this top surface sample. We have also systems that we've tested for that, which include using a drill that goes through the PlanetVac cone, and those tailings that I showed you earlier on the surface of Mars, well, maybe you can take those tailings and instead of doing complex wrist motion using this big clunky robotic arm, maybe you can just use the pneumatics again to pass it all through a tube. So that's another system that we've developed for use in flight as well. So a little more scientifically, the astronauts of Apollo, they were on the surface of the moon and they used drills to varying successes to try to collect core sample, and also try to do some other fundamental measurements on the surface of the moon, one of which is something called heat flow measurements. So I'll move through this a little quicker. But we've also developed a pneumatic system for boring into the lunar regolith. Again, the lunar regolith is a very fine-grained material all over the surface of the moon. It's not, I describe it to people as sand, but it's so much finer than sand. It behaves very dangerously in a vacuum from a mechanism. The electrostatic forces cause the dust to grab onto any metallic surface and kind of stick there and sit there. And if you have too many mechanical junctions, it can wear out that joint. If you talk to the Apollo 17 astronauts and their engineering team, Their spacesuits, when they got back, were over comfortably worn out at some of the joints, at some of the critical joints. So that's because of lunar regolith and how abrasive it is and how dangerous it is to mechanical systems. So this is a system that we developed using a deployable boom to bore into the lunar surface. No drill needed here. We can fire our pneumatics. We can inflate this tube using pneumatics to eject all the regolith out from underneath where those ports are in the lunar surface, and basically cause a big dust flare. You'll see a better image of this coming up. But this slide is here basically to say that we can start this system, bore into the surface, stop at any point, take a measurement there if we desired to, and then resume boring afterwards. Here's a kind of a breakdown of how that works with the pneumatic nozzle at the very bottom of it. So we can mount this heat flow probe, we call it, towards the end of a lunar lander leg. It's very close to the surface. It doesn't have to be on the foot pad. And then it injects its pneumatics, and that tube is forced out through an actuator. It's rolled out and it coils over into a solid tube. And then inside, the pneumatics then is released, causing the material to kick out and kind of excavate a hole in the lunar surface. And we should be able to get about 2 meters deep. Here's one of our higher TRL level designs for that we're testing. And we've tested in one of our 3-meter vacuum chambers. So that big tube there is full of a lunar simulant. And we bored down to almost the bottom of it with using that technology at vacuum pressure. Move through these a little bit. So not to badmouth drills or anything, because we really do like drills. They're very highly capable mechanisms, but they're also very heavy and they take a lot of energy. Another system that Honeybee is developing is our TRIDENT drill, which is going to go on the NASA Viper rover, previously Resource Prospector. This is another very exciting mission that's going to the moon. I believe it was just announced that Astrobotics will be carrying this payload to the surface of the moon. This is part of a larger rover that will drive around on the surface of the moon and collect 1 meter deep drill samples. And again, this is a system that we're developing. So again, trying to make it happen in space, well, you have to do a lot of testing on the ground to make sure it survives the rigors of the environment. So we've done vibration testing, we've done thermal TVAC testing at lunar vacuum and lunar temperatures. And we've also done remote operation tests where we've put the drill on a rover and then operated it hundreds of miles away in Texas from our home station in Pasadena for operating the drill. So just a few more images of what we've had to do to make it all happen, to get it flight qualified. Here you can see an image of the rover where we actually had to put a small simulant bin underneath it for doing our 1 meter deep tests. But again, we're operating this remotely, autonomously, states away, distant that far away. So this is all the testing and preparation work that we've had to do to get this system ready for operations in space. Obviously, there's a big risk here. We're trying to go a meter into the surface, and operating from California and making it drill a meter deep in Texas. If it gets stuck, if there's a problem there, right, we can still send somebody there to unstick the drill and bring it out and make it better, and then the rover can drive on its merry way. Well, not on the lunar surface. If that happens, if the drill were to get stuck or frozen in place, well, now you just have a nice big anchor on your very fancy rover. It's not going to go very far. So again, test, and test. So future sampling missions. So those are ones that are in the queue, and those are more instrument-based. Here's some very exciting future missions that are coming up that we have some sort of involvement with that are related to sampling. NASA also has a very good hierarchy that they've presented in the past for planetary exploration. The general progress has been flyby first, where you think of like the old Voyager missions, where we're kind of just going by as many planetary bodies as we can. Then orbit, you want to orbit those planetary bodies. You can collect more information from orbit. Then you want to land. Think about a lander going onto the surface, right? That's the next level of hierarchy. Well, once you're on the surface, well, you want to sample, right? And then that's where these sorts of capabilities come in. And JAXA is looking at landing on the Martian moon Phobos, and actually returning samples. It's a very ambitious program, very ambitious mission. and they asked us to provide the sampling system for that. So here you can see at the end of that leg, there's a little planet vac cone that's going to collect some sample. And here you can see one of our test setups that we've done again in one of our TVAC chambers, and all the equipment that we need to test, how much force we need to apply, how much pneumatics we need to apply to all this to make that happen. And here's a quick video that I'll show you of what it looks like to do some sampling on a Martian moon surface. So here we're baselining about 10 centimeters off the surface. We're not coming in contact with it. We're in a vacuum, and we're going to start injecting pneumatics directed down at the surface and try to get some of that material to come back through that large tube that we see coming out the back end of that cone. So you see how excited all that material is as we're throwing pneumatics at it, right? And this is from 10 centimeters away. This is not even on the surface. And here's our catch for some of that sample. And I believe in this test, we collected just over 2 grams of material. And again, in vacuum, in these harsh conditions. But it shows all the work that has to go into making something like this flight worthy. So that's again, on a planetary surface that's relatively, near to us, warm, warmer conditions compared to other parts of our planetary solar system. So what's the new frontier? What are the more difficult places to get to? Well, Europa, one of the Jupiter moons, is a pretty cool, pardon the pun, place to go to. And that's going to require a whole different set of sampling technologies and sample handling systems. Europa, I believe, is pretty cold. It's cryogenic ice. It's about negative 260 Fahrenheit, the surface temperature. Which means that there's going to be ice on the surface. It's going to be very difficult, and we don't want it to perform like a Phoenix scoop, right? Where if that ice freezes on our instrument, we're probably not going to be able to get it to unthaw. So we've been doing a lot of work with trying to do testing at such an extreme environment to provide hardware for sampling in such rigorous environments. I believe Jim did an excellent job presenting about Perseverance last month, so I won't go into too much detail, but Perseverance rover for Mars 2020 is very exciting, launching in less than a month now. That's pretty cool to say, less than a month. And that's going to go back to our favorite planetary system, planetary body outside of Earth, which is Mars. And this is basically, Curiosity 2.0. It's not there for the direct astrobiology analysis, but it's there for the sample return. That's pretty cool, right? Because you already did your flyby, you already did your orbiter, you already did your lander. So now you want to say sample return. You want to bring back a piece of that planetary surface, right? That's awesome. Because now not only are you on the surface, you have to get off the surface. You have to get off the surface and you have to get back to your home, right? That's crazy. That's a lot of work. Well, this is the first part of that entire process. And this whole system has the rover, the Perseverance rover, that'll go collect material, it'll cache it, it'll basically drop it on the ground in certain locations, known locations. And then a few years from now, with our international partners, ESA, they're going to provide a lunar rover, a fetch rover, to go grab all those cached samples and bring it back to our MAV, our Mars vehicle, where it will then be launched back up into orbit. This is a really complex process. This is multiple missions to get to the surface of the moon. And this is all based on sample handling and getting that Martian sample back to Earth. Why do we care about getting the sample back to Earth so much? We have something as great as SAM on the surface of Mars right now. Well, truth be told, the SAM instrument was developed over 10 years ago now. It was built over 10 years ago. It was initiated almost 20 years ago. So that mass spec technology is pretty old and out of date compared to what we have terrestrially. So why not use the time that's invested in collecting those samples to our advantage? Why not use that time to develop better ground-based systems here on the Earth? Instead of waiting or letting us wait, we can develop our better technology here, right? So why build a whole new SAM and send it there to the surface when you can just increase your lab capability here and bring the Martian sample back to us? Well, it's pretty hard. As you can see, it takes multiple rovers. It takes a lot of rocketry capability to get back into the orbit of Mars, and then let alone back to the surface of Earth. And that's one of the next big frontiers for sample handling, and that's grabbing a sample in orbit around Mars. This is one of the concepts that's currently being worked on by NASA to make something like that happen. You see the OS, the orbiting sample, in the lower right corner of the screen. Well, that is going to be the sample. That's going to have all those precious Martian samples that will then be ejected by the MAV into Martian orbit, collected by this instrument here, and then it has to be packaged, cleaned, planetary protection standards cleaned, and then repackaged into an Earth entry vehicle that then is sent back to Earth. And that's a crazy process, and that's the next level of what we hope to achieve. It's also crazy to think about that the U.S. as a spacefaring nation, the only time we've ever brought back sample was by the astronauts' hands. The Apollo astronauts brought back sample from the surface of the moon. The Japanese are very skilled at bringing back sample through their Hayabusa missions. They have a lot of flight heritage and experience in that. So Mars sample return will be one of the first systems that we'll have to bring back sample robotically from another planetary surface. I believe the first one that'll claim that title will be the OSIRIS-REx mission, but that's a story. Go ahead.
We have a question on the chat. What about weight considerations in your designs?
Mass is always I'm not going to call it a problem, but it's always a concern. The biggest resources we care about when we're developing mechanisms for flight are mass, volume, and energy use, and then the CONOPS, the concept of operations for that. And CONOPS involves things like the duration that the instrument has to be on for, how much data it'll process, and how much data it'll generate that then has to be transmitted back to the surface. But yes, mass is always a debate, especially when you're building such complex instruments and rovers and landers. Designing for minimal mass is very important. Now, let's say you have the biggest rocket you can think of, right? And maybe that's what you're going to launch on, right? Well, then maybe your mass problems go away, right? Because you have a really big, expensive rocket, and that expensive part is really the problem. And that's what really is the other factor to all of this spacefaring and space science work, the financial cost. And that's kind of why, the CLIPS program is existing, and why the commercial resupply of the ISS exists, to try to drive those costs down for bringing payloads to the ISS, bringing payloads to the surface of the moon. I didn't mention it before, but the CLIPS program is really there to try to make the surface of the moon the next ISS test bed. The International Space Station does a lot of really great research work, but it's still very expensive to get there. There's a lot of other scientific information that we can get from the surface of the moon and doing work there to develop our hardware and our capabilities. So minimizing the amount of mass that you can send up into orbit is very important for cost reasons. And then you start talking about getting to the surface of the moon or Mars. Heavy things won't get there. And you start talking about bringing things back to Earth after all of that. Yeah, it better be really lightweight and very small, because trying to bring back takes a lot of energy. It takes a lot of energy. It takes a lot of cost. If it costs too much, it might not happen.
Okay, we have one other question. Mars Insight has some difficulty with this drill. Would you please expand on that?
Yes, so that's called the mole. I think it's M3, if I remember correctly by the technical term, but we affectionately call it the mole, and it's a self-propelled hammer. It percusses on its own to bore its own hole. Inherently, it's not a bad idea. But the problem with it is, what happens if you hit a rock? What happens if you hit something that's solid? Well, if it's small enough, you might be able to just percuss and get around it. If it's too big or too dense there, then maybe it's going to hit it and it's just going to rebound and it's going to bounce off. If you've ever dug a post hole, especially in the New Jersey soil, you probably come across a lot of rocks, a lot of granite under the surface. So you need to go get a nice big shale bar, right? And go beat this rock with a shale bar and try to break it up. Well, that's a lot of effort. That's a lot of energy. That's a lot of work. And that's what the poor mole has to deal with. It's not going to break the rock. It doesn't have enough power to break the rock. So in some of those images that you've seen come back from the InSight of it rebounding outside the hole, that's more than likely what happened. It hit something hard under the surface and it bounced out. And even worse, it's possible that some of the hole that it created collapsed in, causing it to have to re-burrow through its own hole again. So that's some of the difficulty that the mole has experienced. So I can continue on. I think this is one of the last main missions that I was going to talk about. Save the most exciting for last, right? This is one of NASA's newest missions, Dragonfly, which I'm also working on for Honeybee. Honeybee's got a pretty nice part about this system. For those of you that are unfamiliar with Dragonfly, it's really cool. It's basically a nuclear-powered quadcopter that's going to land on the surface of Titan. That's a pretty cool thing to say. You can think of it as a flying Curiosity or Perseverance rover. So how do we get away with that? Well, on Mars, we can't fly very well because we have a very thin atmosphere. Perseverance will have a little rotorcopter on board called Ingenuity, I believe. And that'll kind of prove some of the flight ability on the surface of Mars. But Dragonfly is taking that to a whole other level. It's a quadcopter on the surface of Titan. This really increases our mobility. So one of the things I left out when I mentioned that hierarchy of flyby, orbit, land, and then sample return, I kind of omitted rove, drive, reposition yourself on the surface after you landed. And that's what Curiosity, Spirit, Opportunity, all the Mars rovers have done, and then that's what Dragonfly is going to build off of. But instead of driving across the surface, it's going to fly across the surface. That's because the surface of Titan is about 1.5 times the density of the Earth atmosphere. So it's much more capable for flying using propellers. That's pretty cool. Second, you got a lot less gravity as well to compete with. Increased atmospheric density, lower mass. Hey, get me a good aerodynamicist, and I think we can design some propellers that'll work on that system, as long as you can minimize your mass and make sure that you can combat that force balancing equation for flight. And right there, that's how the Dragonfly concept was born and developed. So on board Dragonfly, we're going to be carrying a very similar to SAM instrument called DRAMS, another mass spec that'll analyze the organic compounds that we expect to find on the surface of Titan. So as part of that, we need a drill. We need something that can do the sampling for that. So one of my colleagues made a very nice video that's about 3 minutes long that I'll share with you guys that does a much better explanation of how this sampling chain works. So if that is looking good to you guys, I'll go play.
It's good.
Titan is the only ocean world in our solar system with a dense atmosphere, and the unique organic chemistry that takes place on the water ice surface makes it an ideal location for such a search. To study Titan's composition, Dragonfly carries onboard science instruments that analyze ground material from numerous landing sites across Titan's surface. Draco is a robotic system on Dragonfly that acquires samples of surface material and delivers them to the science instruments for analysis. Draco is comprised of 4 unique subsystems. Redundant sample acquisition drills extract material from the ground. The pneumatic transport system moves that material inside the vehicle. The sample delivery carousel presents that sample to the instruments, and avionics orchestrate and automate the process. Honeybee Robotics has developed a full brassboard end-to-end sampling testbed to demonstrate Draco's performance. Sampling is a 6-step process whereby ground material is excavated, transported inside the vehicle, and ultimately delivered to the science instruments. As a first step, Draco can take preliminary measurements of the surface by drilling a shallow hole. Drilling data and close-up images of the cuttings help inform the decision of whether to continue sampling at that location. Next, Draco is configured using pneumatic valves to select which drilling site to investigate, which blower to vacuum up the cuttings with, and which instrument to use for scientific analysis. The carousel then moves one of 58 single-use sample cups into the collection chamber, and the system is ready to acquire a sample. Before drilling, the selected blower spins up to cool down the pneumatic tubes with cold Titan air. As the rotary percussive drill bores into the surface, the cuttings are sucked up and rapidly transported through the tubes, just like in a household vacuum cleaner. The vacuumed up cuttings fly through the system in a fraction of a second. As the sample passes through the collection chamber, a mesh plate deflects the particles into the sample cup, where they are trapped. Excess sample simply passes by to be ejected outside the vehicle by the blower's exhaust. Phase A testing in a near-Titan environment has demonstrated this collection method to be gravity agnostic and robust to cohesive simulants. After the cup is full, the drill retracts out of the borehole while percussing and spinning to remove any built-up material from the drill bit and pneumatic inlet. The The blower then flushes out residual material from the tubes and is spun down to a stop. To complete the process, the filled sample cup is removed from the collection chamber and positioned at the corresponding instrument chamber. 4 elevator mechanisms in the warm zone underneath the carousel lift and lower sample cups. The sample cup hermetically seals to the instrument through a knife edge interface. Draco can deliver sample to either of the 2 instrument modes that Dragonfly is equipped with to analyze material taken from the surface. In gas chromatograph mode, the sample is heated to release volatiles that flow into the mass spectrometer, where their composition is determined. In laser desorption mode, a laser ionizes the sample through a thin mesh window, and the liberated ions are ingested into the instrument. The cup can be repositioned to take measurements at multiple locations for improved accuracy. We don't know how life came to form on Earth, but the science that Dragonfly will do on Titan could provide a key piece of that puzzle. Draco has been engineered to empower the Dragonfly mission in its search for life, answers, and understanding.
Steve, we have another question.
Happy to answer it.
Do the vehicles or probes need to generate any internal heat to function?
Yes, that's a good question. Thermal conditions.
Drifting alone through the darkness of space.
Did you hear that?
Capsule
Sorry.
The void.
See if I can stop that.
The 2 pioneers prepare for the next step.
That YouTube video thing. Sorry about that. Yes, thermal conditions are always and that's actually the part of the brilliance of using that nuclear battery, the RTG, on Curiosity, on Perseverance, and on Dragonfly. The RTG generates a lot of heat, and it also generates a lot of electrical power, but we can also use that thermal energy to keep us warm in these environments, hence saving us extra energy. Solar panels are great. Solar panels are nice, reusable, regenerative energy producers. However, they take a lot of, if you're trying to use solar panels and you have heaters, you're going to burn your batteries pretty quick. Something like the RTG, though, generates a lot of heat inherently, and it generates a lot of power. So using both in one resource is a pretty cool use, pretty cool capability.
Okay. I personally have a couple of questions. Is there more slides to your presentation I should ask first?
That's pretty much it, but I'll just say one last thing about Dragonfly, and I'll happily answer the questions. But so right there, that little video that my colleague Ty put together and spoke about is kind of the culmination of everything else that I talked about earlier. I think in the Dragonfly sampling system, you saw that there's pneumatics involved, there's drills, there's that carousel similar to SAM on the sample SMS, the sample manipulation system on MSL. All those things are kind of put together in Dragonfly, making the Dragonfly mission really the culmination of the state-of-the-art in sampling technology that we have going forward. This will be really exciting. It's the great future. Should launch in 2026 and get there somewhere in the 2030s. So it will be a long mission that'll last a long time. We're really looking forward to it. So thank you all, and I'm happy to answer the questions.
All right, thank you very much. Just a question, can you talk about your educational journey that got you to where you are today? I mean, there's an incredible amount of design and engineering that you showed us tonight. It was simply incredible. How do you prepare for that? What are the requirements? Could you talk about that for people considering making the journey? Happily.
First, I'll say, obviously, it's not just me. It's a lot of other very smart, talented people. It's a lot of very smart senior people that have a lot of experience and expertise in very specific niche topics. And it's interesting to run into these types and what their real passions and interests are. Because if you're studying those passions and interests in school, then I don't even know who you are. That's crazy. In the education system, you learn things as general as chemistry and biology. You don't learn anything half as specific as astrobiology, right? In a curriculum. And a lot of that capability, or a lot of that education and that knowledge is through experience, through trial and error, through practice, getting in the right positions to have those experiences and that knowledge, working with the right people, and having them share their information with you, and you gain from that. Experience is non-transferable, and that's part of what's so valuable. I started at Voorhees High School just down the road there. I took an interest in science and engineering pretty young, and I kind of knew I wanted to go into engineering, specifically mechanical engineering. So I actually went to Rutgers, and I did my undergrad and a master's degree there with Dr. Chaim Benaroya. Dr. Benaroya was excellent, really terrific, and his whole specialty is lunar structures. That's one of the things he's very passionate about. Obviously, we don't have any structures on the moon, so maybe it's not that applicable today, but maybe it will be tomorrow. So I was actually studying something in my master's that's completely irrelevant for current application, right? But that's the truth about a lot of things in school today, and a lot of college and higher level degrees. The truth is you don't know what you're going to be doing 5 years from now, 10 years from now, 20 years from now, right? So the best thing you can do for yourself is take an interest in learning and advancing your own questions, your own desires, your own things that you want to know more about. Follow your passions, follow your interests, and then pursue them to the best of your ability. Meet the right people. The best things, some of the best experiences I had as an undergrad and earlier than that were figuring out what I didn't want to do. So I tried a lot of different activities because it's much easier to determine what you don't want to do than what you do want to do. So try a bunch of different things. Don't be afraid to fail. Don't be afraid not to like it, but do it and get an experience from it. Again, experience is non-transferable. You now know something more about that topic, and then maybe you'll be able to apply it later. Learn everything as quickly as you can. That sounds like a horrible thing to do, right? But really, the more things you understand earlier, the more applications you could have for that information down the road, and you may not even know what that application might be. So yeah, in my master's degree, I did lunar structures, and structures are static. That's not robotics. But I also did a couple of internships, applied internships as a college student for sure. And I was fortunate enough to have a NASA internship at Goddard Space Flight Center doing robotics. I was actually at the NJAA, I guess about 10 years ago. I'm embarrassed to say that long ago. And I did a presentation about my NASA internships experience. I was looking through my old slide pack and saying, wow, that was a long time ago, but I did a lot of cool work at that point. And at that point, I kind of understood that was kind of the topic I wanted to do, thanks to those internship experiences. And that kind of put me on the road of, pursuing this sort of scientific information that I was curious about, and what it would take to work in that environment. And thanks to Dr. Benaroya, I was able to get in touch with my current boss, Dr. Chris Zachney, who is the first planetary PhD in extraplanetary drilling. Again, a very narrow, specific topic that at the time, nobody was doing that except the astronauts, right? And now we have a very successful research work and flight instrument development path that we're putting forth for enabling some of these planetary science missions. So we're looking forward to exercising a lot of those capabilities going forward. But yeah, follow your interest, follow your passions. Don't be afraid to fail. Don't be afraid to find things that you're not interested in, because things you realize are not of interest will help you point to what you actually want to do.
All right, thank you so much. We are privileged to have you present tonight. We love having people that are members of our organization, and to have you join us and present this fascinating material tonight was just an absolute privilege. We thank you so very much. There are no further questions. Oh, everybody is saying thank you. Thank you very much on the chat. So we look forward to doing this again sometime in the future.
Me too.
All right. Thank you very much. I'm just going to close down the stream, and I'll be right with you, okay? Stand by.
Take care.